We know that 2 multiplied by 2 multiplied by 2 can be written as 2 to the power of 3, which is 8. So the operation that we did here is called exponentiation, or raising a number to a power. Suppose we want to look at the inverse operation. Suppose we have this equation here, 2 to the power of x equals 8. So the inverse operation would be, what number must we raise 2 to in order to get 8? Now this number here is referred to as the base. We say that the logarithm, or log for short, of the number 8 to base 2 is x. So we write it like this: the log of 8 to base 2 is x. So finding x is the inverse operation to raising 2 to the power of x. Of course, we know the answer is 3. So if we want to write this log statement as a statement involving powers, we say that 2 to the power of 3 is 8. So this number is the base. Here's another example. Suppose we want to get the log of 2 to base 2. That means what power must we raise this base to in order to get this number 2? And the answer is 1, because 2 to the power of 1 is 2. Here's another example. What power must we raise the base 2 to in order to get 16? And the answer is 4, because 2 to the power of 4, 2 to the power of 4 is 16. 2 2 is 4, 2 4 is 8, 2 8 16. What about log of 1 to the base 2? Well, the answer is 0, because any number raised to the power of 0 is 1. 2 to the power of 0 is 1, and indeed any number to the power of 0 is 1. Here is another example, this time involving base 3. The log of 9 to base 3 is 2, because 3 to the power of 2 equals 9. The log of 81 to base 3 is 4, because 3 to the power of 4 is 81. Here's an example of a log to the base 10. Log of 100 to the base 10 is 2. Now, the function log to the base 10 of x is on most scientific calculators, although the base is often left out. The base is understood to be 10. So the button will usually just say, will just have log written on it, meaning log to the base 10. Log to the base 10 of 1000 is 3. It's just a matter of counting the zeros. Log of 1 to the base 10 is 0, because 10 to the power of 0 is 1. Any number to the power of 0 is 1. What about log to the base 10 of 0.1? Well, that's actually minus 1. 10 to the power of minus 1 is 1 divided by 10 to the power of plus 1. 1 over 10, or 1/10, is 0.1. Similarly, log of 0.01 to base 10 is minus 2, because 10 to the power of minus 2 is 1 over 10 squared, or 1 over 100, which is 0.01. Let's look at the graph of f of x equals 10 to the power of x. Now this graph, this function, is the inverse of the function log of x to the base 10. Let's evaluate the function at x equals 0. So we get 10 to the power of 0, which is 1. So this point here on the graph. So the graph of f of x equals 10 to the power of x crosses the y-axis at 0, 1. Let's evaluate f at a very large negative value of x, say at x equals minus 100. So f of minus 100 is 10 to the power of minus 100, which is 1 over 10 to the power of plus 100. Now that's a 1 over a 1 with 100 zeros. So it's an extremely small number. It's practically 0. but not quite 0. So what is actually happening is that as x becomes smaller and smaller, or as we take larger and larger negative values for x, the graph of 10 to the power of x will approach the x-axis, but never actually cross the x-axis. So this graph is always positive. So f of x is always greater than 0 for all values of x. So only part of it is shown here, but this graph approaches the x-axis asymptotically. Now let's look at the graph of log to the base 10 of x. We can call it f of x for a general function, but since we refer to 10 to the power of x as f of x, and since this function is actually the inverse function, we could write it like this to indicate that we're getting the inverse function of 10 to the power of x. Let's work this out at x equals 1. Well, you've seen this already. This is log to the base 10 of 1, which is 0, because 10 to the power of 0 is 1. So when x is 1, y is 0 for this function here. We could work out this function at x equals 10. We would have log to the base 10 of 10, which is 1, because 10 to the power of 1 is 10. Now, it's not shown on this graph here, but if we could extend this x-axis to x equals 10 and go up to the graph, we would hit the graph at the point with coordinates 10, 1. So you can see that for all these values here, the value of the function is less than 1. But if we extend on to x equals 10, this graph will cross the line y equals 1. Now we can construct the graph of log to the base 10 of x from the graph of 10 to the power of x by reflecting this graph through the line y equals x, or f of x equals x. This line here has a slope of 1. See, it's got the form y equals 1x plus c. C is actually 0. C would be the y-intercept. So it crosses the y-axis at 0, so this line goes through the origin. This number here is the slope. So the coefficient of x is 1. So that means that if we pick any point on the line and increase x by 1, then y will increase by 1. So this line actually makes an angle of 45 degrees with the positive x-axis, because we have an isosceles triangle here. Both sides are the same. If you take any point and reflect it through the line y equals x, you will reverse the coordinates of that point. And that's exactly what we want to do here to get our inverse function. We want to reverse the coordinates of a point. So if we get the image of 0, 1 under axial symmetry in the line y equals x, we end up at a point whose coordinates are 1, 0. We just reverse these coordinates. So we move the point 0, 1 at 90 degrees through the line y equals x. So it's equivalent to folding the plane over this line, if you like. So if we fold the entire plane over this line, then this graph will fit down exactly on the graph of log to the base 10 of x. Now, as I said earlier, if all points on this graph are above the x-axis, so if we take any point, say further along here, it's going to be above the x-axis, any point on this graph. That means if we reflect it through the line y equals x, we're going to get a point that's in this quadrant down here. So that means that the graph of log to the base 10 of x is asymptotically approaching the y-axis. So it never actually crosses the y-axis. So that must mean that this function is not defined for negative values of x. For example, suppose we try to work out log of x to the base 10 at x equals minus 1. Let's suppose we try to do that. And let's suppose that that's equal to y. That means that 10 to the power of y equals minus 1. Now, there's no solution to this, because if we raise 10 to any number, we always get a positive number. Because we see that from the graph. If we raise this graph is above the x-axis. It's always positive. All the y values are positive. 10 to the power of x is positive for all numbers, values x or y, whatever, it doesn't matter what you call them. So there are no solutions to this. That's true for any negative number. Well, if you're not convinced, I mean, 10 to the power of any positive number is a positive number. 10 to the power of 0, as we know, is 1. If we take 10 to the power of any negative number, say 10 to the power of minus 1, well, we just get 1 over 10 to the power of plus 1, which is positive. So you can see that 10 to the power of any number is always positive. So the log function is not defined, or basically doesn't have any real values for negative values of x. Let's suppose that we want to get log to the base 10 of 4. So we want to find the coordinates of this point here. Well, you can do that on your calculator. Just go to the log button on your calculator. So here it is. This log button means log to the base 10. So you put in 4 and then press this button, or vice versa actually on most calculators. You press the log button first, then 4. You can see that we get 0.602 to 3 decimal places. So that means that 10 to the power of 0.602 must equal 4. If we reflect this point through the line y equals x, we reverse the coordinates. So we get the point 0.602 comma 4. In other words, 10 to the power of 0.602 equals 4. So 0.602 is around here. So the log to the base 10 of 4 is 0.602, and 10 to the power of 0.602 is 4.